Good afternoon, everybody. This is Tom Sheen again in Boston at Northeastern University, and I'd like to go ahead and get started. I want to welcome you to today's webinar that is part of the webinar series for the Sustainable Adaptive Gradients in the Coastal Environment, or SAGE, research program, which is an NSF-sponsored research coordination network project that's led by Elizabeth Hammond at UMass Amherst. We're very pleased for this webinar to have Dr. Robert Weiss, who is an associate professor in the Department of Geosciences at Virginia Tech. Robert he's been on the faculty there since 2008, first as an assistant professor of geology and geophysics, and as of 2011 as an associate professor of geosciences. He graduated from the Westphalia Wilhelms University in Münster, Germany, with a doctorate rare not, which is the equivalent to a PhD in the natural sciences, and received that in 2005. Right after that, he was a research scientist at NOAA in their Center for Tsunami Research from 2005 to 2008. His research is focused on understanding the response of the physical environment to tsunami generated by earthquakes, slides, and oceanic meteorite impacts, and the records that such processes produce. We're really pleased that Robert is going to be talking today about the impact that tsunamis and storms have as major agents of coastal change and the threat that they pose to coastal communities and civil and military infrastructure and to economies. As an administrative item, if you have a question for Robert that we will be taking at the end, the best way to do this is to have you put that into the chat box and address it to the host. You can also deposit these in the Q&A tab on your interface for the WebEx. If you're having any technical problems during the talk, please send a chat to the host, the College of Engineering at Northeastern University, and we'll try to address those as quickly as we can. And with that, I'm going to turn it over to Robert for today's webinar. Robert.
All right, thanks very much, Tom. Can you hear me all right, or is that still a problem?
The sound here is good, so I think it's, once we have, if there's problems with the audience, they can send a chat to us and we'll let you know.
Okay, thank you very much. So today I'm going to talk to you about how we go about decrypting some quantitative information from the deposits that storms and tsunamis leave behind. And if we talk about deposits, then what I mean is we look at the entire spectrum of grain sizes that are involved in this. So this is a table that is a very standard table, and you find that in any sort of sedimentology or geoscience textbooks, which gives you sort of a grain size and the associated aggregate names, for example, boulders or sand. What we're going to do today is we're going to focus on boulders, and we're going to focus a little bit on sand, and I will talk about the methods that we use and develop in order to retrieve quantitative information from the deposits about the causative event and what the problems still exist with it. So first, we're going to talk about boulders, and when I talk about boulders, you have to go and imagine a situation like this. This is Samoa in 2009. And you see these blocks here and there. They are boulders, and you see here that boulders are moved and laid down as a field, so you can study the distribution of boulders. Some are smaller, some are larger. But what we associate with boulders is this, and that's a very significant boulder of about 1, 2, 3, 4, 4.5 meter height, and so forth. So this is the house-sized boulder that is moved during very, very large tsunamis and storms, whereas the boulders in the previous slides can be moved by smaller events. The reason why we look at boulders is because no other more common marine process can move those boulders. Therefore, they have a very high preservation potential, meaning that they cannot be moved afterwards. And if they're preserved well, in the geological record especially, then we can use those as indicators of previous events. The reason why this is important is many coastlines feature tsunamis and storms. And here you see the coastlines that are impacted by storms. And that means that if you look into improving hazard assessment or risk assessment, and then therefore we need to improve our hazard assessment. And if you look into the history of how many tsunamis, for example, how many storms occurred in the past, in the recorded past, fortunately or unfortunately, depending on what side you're on, there are not enough not enough tsunamis and storms have occurred in order to come up with a very, very meaningful statistics of it. So we need to go and interrogate the geological record for storms and tsunamis in order to make a really, really robust statistics. In coastlines, where both of them are sort of competing agents of change, you need to discriminate between the two records. And that's extremely, extremely difficult. And that's one of the tasks that we have, not only figuring out how many tsunamis or storms occurred in the past, but also we need to sort of distinguish between the two, which I will tell you in a little bit is actually the bigger problem of the whole thing. So in the next few slides, I'm going to show you some very intuitive approach to a modeling our modeling software that we develop here. And so you will see a lot of circles and a lot of very simplified geometries. And I do like the circle or the sphere for theoretical reasons, because we can very simply use angles and rotation and move our normal rectangular understanding of the world into a cylinder coordinate system that allows me to simplify the equations quite a bit. So this is the initial position of the boulder, and the boulder has a radius, and the boulder lies in front of roughness, and that prevents the boulder from rolling down that little slope. That also will prevent any given flow to move the boulder, so it provides some sort of resistance. For the boulder to move, it has to overcome this roughness here and rotate in this very simplified view a angle that I call theta c, a critical angle. You see here the equation that it is used to do that, and the input to that critical angle is essentially the angle of the slope on which the boulder is resting, and the height of the roughness elements that is in front of it. So, and for figuring out the equations, we go back to the old Newton's second law of motion, the sum of the forces on the left-hand side, and the reaction, the mass and the acceleration on the right-hand side. The beauty of this approach is because we have spheres, and we can rotate those spheres out, and therefore we can transform the coordinate system from a Cartesian, like our usual understanding of the world, into a very, very simple one. That allows us to write one equation instead of two equations for the motion of the boulder. Instead of writing an equation for x and an equation for y, for the y direction, we only have to write an equation for theta, and that's essentially what you see. So this is the acceleration of the boulder. This is the acceleration of the boulder out of the pocket. And this is the sum of the forces that assumes it. And we can do that because we assume the radius of the boulder doesn't change during the motion of the boulder. On the right-hand side, because we are in water, we need to import a few things here. We need to add this to it, which is essentially take into account that the boulder has to displace the water in order to move. Then we can go further. On the right-hand side, we see the sum of the forces, and in very classical approaches, if that sum of the forces was larger than zero, that was used as an indicator that the boulder has moved. And that is true. If drag, lift, buoyancy, and weight, if that sum of these forces is less than more than zero, the boulder will move. And a little cartoon of that is presented here in the following slides. So I assumed an angle of alpha of the slope as 0, so that a flat horizontal area. Delta is 1, which means that the roughness in front of the boulder is the same as the radius of the boulder. And in order for the boulder to dislodge, it has to overcome this radius and be in a position that is indicated here with the dashed circle. As you can see here, at this present stage, it hasn't moved yet, so theta is 0, and the sum of the forces is less or equal 0. So it's resting still in place. As we go forward, we see that now now it is between 0, the boulder has moved, and the angle theta now is in between 0 and critical C. But the sum of the forces now is larger than 0. If the force, if the driving process that generates the sum of the forces being larger than zero would go away, so that the sum of the forces will go back to 0 or less than 0, then the boulder would start moving back into his pocket again. So we couldn't even see whether the boulder moved or not. And so, as the boulder moves towards this second dashed circle on top of the step, the sum of the forces have to remain above 0 at any stage of this. If the forces, the sum of the forces will go 0 or less than 0, then the boulder would always rotate back into its original position, and eventually it arrives here. Here at the slide before, even in that stage, if the boulder would move back to its original position if the forces would be less than 0 at this stage. Only at this position, the boulder would start to dislodge. And that takes time, and that means that the forces have to be maintained above a certain threshold for a period of time. And that period of time is related to the period of the waves that move it, either a tsunami wave or a storm wave. And that is, and for the threshold, we can use, instead of simply the sum of the forces, we use essentially the impulse. This is what that is, and say if the critical impulse is exceeded, then we have boulder dislodgement, and instead of just saying, oh, it's the force or the shear stress. But that's just on the side. The impact, the input for the respective driving forces, as in storm or tsunami, I want to present briefly a storm case. So this is our impact, our input. And you can see it's not just a single wave. Actually, we use a spectrum of waves and use a nonlinear model that transport energy across a shelf. So here you see the very simple setup, geometrical setup. So it's a steady slope. It's a single slope that goes from the right side of the domain to 0 at the shore, and this is the input spectrum. So not just one single wave, but the whole wave spectrum. And then down here, the equation, as ugly as it might look, is actually very, very beautiful. Because it's physically very simple. It describes nothing else than the interaction of 3 waves with each other. And then what is the resulting interaction of that? So yeah, it has an E and a minus E indicating complex numbers, but mathematically speaking, it's actually quite a bit easier to use this equation than actually try to write it out in the physical domain. So this equation works in what we call the frequency domain. So we just look at the frequency along this and compute the different components. So if you run this model, which is very cool, we get this would be a result, for example. So what you see here is on the left side in Figure A, you see the blue line is the input spectrum, and then the red line is the average, and then indicated in the gray shade is sort of the minimum and the maximum, or what we can expect, because we don't only have the ability to run one model run, so one specific spectrum. Because it's a spectrum, we don't know exactly how the different frequencies are placed to each other, which means the waves we don't have information of the phase of the waves. So we run 100 different realizations of the same spectrum and assume random relative phase shifts between, so that the results can be quite different. While the results for the main waves in this area are pretty much the same, and you can see that because of the width of the gray shaded area is very narrow, whereas in this area here it's pretty wide. So we almost have 2 orders of magnitude different in this area between the maximum and the minimum, and that is an important sort of information. Left of the dashed area here, you see this little f sub I, and this is the area that we call infragravity band. So everything that's beyond 30 seconds, a little longer than 30 seconds, is called infragravity. And you will see here this. What you need to look at here is this dashed line. Is this red line here? You see here it's in this area, but if you move over here to B, that is in 15-meter water depth, the red line has moved up a little bit. And if we go from here over to C, which is in 5-meter water depth, then again we see that the red line has moved up a little bit. That means that the energy, the amount of energy that is in the infragravity band, meaning in wavelengths wave periods that are longer than 30 seconds, is higher here compared to here. The question is, where does this energy come from? And it comes from this energy. From this frequency band, meaning that during the process of the wave propagation from 20 meter into 5 meter, energy is shifting from the shorter waves towards the longer waves. And that can only be done if you assume nonlinear waves. Our sort of single wave understanding of the world does not allow that to happen. So instead of thinking about waves, we think about frequencies and how they exchange energies, and that's a very nonlinear process that is very difficult. So if we integrate from here to here for the entire domain, we get an idea of the energy that is contained in the spectrum. If we integrate from here to here, we get the energy that is contained in the infragravity band. That means if we divide these two numbers by each other, we can get sort of a ratio between the two. And that's what this equation down here essentially shows. And we see here that the ratio in figure A is about 10 to the power of -4, in B 10 to the power of -3, and in C 10 to the power of -2. While this is still very small, the interesting thing is that between these 15 meters of wave propagation, the energy in the infragravity frequency band increases by 2 orders of magnitude, by a factor of 100. And that is significant because that means something happens with these waves, that longer wavelengths become more and more important, and that has consequences for the velocity field that boulders or other sediment experiences. Let's look at that. Let's look at the resultant velocity time series for this. So what you see here is in the first line, A to C, you see the converted velocity as a function of time in 20-meter wave, 20-meter water depth, 50-meter water depth, and 5-meter water depth. So I just plotted 3 of the 100 realizations, and you see that they're pretty wiggly, I would say. On the lower one, on the lower row of pictures, D, E, and F, you essentially see close-ups between 50 and 100 seconds instead of from 0 to 600 seconds. So focusing on the lower ones, can I zoom in? Yeah, this is awesome. So if you, this is why I like giving talks with the iPad, because you actually can zoom in. So if you look at that 20-meter water depth time series between 50 and 100 seconds, then you will see that the individual realizations of the waves have very different time series. if you follow the solid line, you will see a difference to the dashed line and to the dotted line. So, but you see that they are more or less at the same sort of amplitude or same crest and same trough. And that can be also seen in Figure A, where you see, so you can almost draw a line here, and you see there are very little waves actually exceed that. So there's not much variation in there, or there are not many outliers in there. So now, if you focus onto the second one, E, meaning in 15-meter water depth, you see that the number of outliers sort of increases, meaning that wave-wave interaction produces conditions that create extreme waves for very short amount of time, and those extreme conditions are different for the different realizations of the same spectrum. For example, if you look at this one here, you see there's no black line, no solid line, or no dotted line around, or here the same, or here. So that is nice. So we have more extreme wave conditions as we move closer to the shore, and you can sort of see that also in this figure here, where we have more things sticking out all of a sudden. And then we move to the 5 meter. And the 5 meter becomes really complicated. You see that none of the waves none of the realizations overlay each other anymore. And we have more and more outliers. But also what you see is, if you're here, this is 0. If you look at the amplitude above this area and the amplitude below, you see that on average there's a little skewing going on. So we have a larger amplitude up on the wave crest, and we have a lower values in the wave trough, and that's because of the interaction with the bottom that is getting closer. And you can see that here too in the upper picture, where sort of here 0, and you see that there's a slight asymmetry between the positive and the negative value of the horizontal velocities. So now we have 100 of these realizations of the same time series, and that needs to be coupled with the boulder that moves. So now, if you, for example, go to 5 meter water depth, zoom in one more time, and now we apply, let's say, the solid line to a boulder, and see if the boulder moves or not. We don't know that yet because simply it's too complicated to predict that from this plot. And now we look at let's say, the dotted line and do the same, and the dashed line and do the same. The question is, for any given mass, will the boulder move at the same time for all of these realizations? Probably not. And will the boulder move at all, or dislodge at all for all realization that is possible? And it turns out that this is actually quite interesting because of the following. We go to the next slide, and we see this plot. And you see here on X is mass, and on D is what we call the frequency of dislodgement, meaning how many boulders of the 100 realizations actually dislodge for the same mass. So we use this equation for an ND is essentially the number of realizations for which the boulder dislodged, and N is the total number, which is 100. Very simple. So, for example, and that's related to the mass. So, if the boulder is 1,300 or 1,400 kilograms or less, then more than 95%, more than 95 of the 100 realizations will cause boulder dislodgement. For 4,600 kilograms, 4.6 tons, about 50% will dislodge, meaning that is exactly 50%. So that's the median. And if the boulder is heavier than 8,000 kilograms, 8 tons, then less than 25% of the realizations will cause boulder transport. And it doesn't matter if we use 1,000 or 100 as the base number here; it will always be a plot like this. And that is that also goes away from the original sort of idea that one wave moves one boulder, because of these realizations, because of these many realizations and the statistics behind. That means the nonlinear interaction between two waves or three waves or many waves in this case may create a situation that even though the individual wave would not be able to move a boulder, the combined interaction of three small waves could theoretically generate a condition that could move a boulder even though the individual could not. And on the other hand, this is also wave theory, the interaction of three large waves could create a condition above the boulder that for waves that usually would move boulders individually, and it's not moved because of the interaction of the wave diminishes the velocity. So it becomes relatively complex very quickly, but it gives you a sense of the complexity that is involved in this even very simple consideration that this still is. So now I'm going to show you a picture that is my biggest pride, so forth. So this is a picture that involved, and it literally I implemented this into the presentation 10 minutes before this talk started, because that's when my computer finished this picture. You see here, let's focus on this here. What you see here is on axis roughness, on Y we have mass, and you see three different panels in each figure, and the roughness goes from for each of them from 0.1 to 1, here 2, and as well. And that indicates different angles, different slope angles, for example, of the shelf or the beach. And then the different rows indicate different wave conditions in the input. So the significant wave height at the right border, at the right boundary of the model would be for this location would be 2 meters and 8 seconds in amplitude and 8 seconds in period. And if you go down here, you have 8 meters in amplitude and 16 seconds in period, traveling over different slopes. So in the blue indicates that no boulder was moved, or fewer boulders were moved. If you are sort of in the green-yellow area, that means 50-50. 50% of the boulders were moved, so the frequency of dislodgement is 50. And if it's red, then all the boulders were moved. So you can sort of, this is a three-dimensional image of the one figure that we saw in the last slide. Yeah, so this is an incredible picture, and it contains about 60 million model runs. So 60 million individual model runs go in that picture, and it took exactly a week to do that. How this is ordered is the following: the amplitude increases in vertical direction, and the period increases in horizontal direction. So we have 8, 10, 12, 14, and 16 seconds, and 2, 4, 6, and 8 meter resolution. The reason why we don't have anything down here in this area is the conditions are such that the waves would start to really break, and that generates flow conditions that would violate some of the theoretical constraints that we have on the boulder. Otherwise, we had to run really three-dimensional wave models, and you couldn't do this amount of you couldn't do the amount of simulations that we would like to do for this with these complicated wave models. Okay, let's focus on the results actually. So you see here expectedly that the masses of boulders moved by small amplitudes and short wavelengths are very low. So most of the area in these plots, I can zoom in, of these plots is blue, meaning 0. A few boulders were moved down here. So here, for very low roughnesses and a very steep slope, this would mean that all the boulders were moved. And as we move to longer periods, we see that we have more and more red in this figure, and we're focusing right now on the first set, on this set. Okay, if I move through, so we see more and more red in this. But what you also can see is the influence of the roughness, and that's why I have this in there. Otherwise, you would see, for example, here a straight line, but if you look careful, they are slightly bent. So that means the roughness has a significant input, significant influence on this. So if you go to 4 meters, the transition between where 50% is at about 50 kilograms or 60 kilograms for a wave with 4 meters of amplitude and with an input wave of 4 meters of amplitude and a period of 8 seconds. But if you look here for 4 meters of amplitude in 16 seconds, we go in the order of 100 kilograms or more. So you see how the period has an influence and how the 50% or the 100% frequency of dislodgement increases from about here to here. So from here to about here. So an order of magnitude it increases. And you see the same for 6 meters in 10 seconds. You go from here, 50, to about here. Now the problem is if you compare these values here and these values here, and you assume some sort of some uncertainty, then you arrive at the conclusions that you no longer can determine what wave actually moved the boulder, because you have, it could either be a wave of 4 meter and 16 seconds, I mean, I'm talking about the input wave, or a 6 meter wave of 10 seconds. Or you could even go further and then involve the slope. So we are less and less certain, and we need to analyze these uncertainties. But before we can analyze them, we need to be made aware of, and that is also a problem at the moment. So we move from, let's say, from here to here, and we see that the mass increases logically. And then if you go to this wave here, then we obviously see a big mass increase. And now from, let's say in this area here, we can move boulders that are tons of, instead of kilograms. So you see how by changing from here to here, quadrupling the amplitude and doubling the period results into boulder dislodgement from kilograms to tons. So you can see the nonlinear relationship between the parameters describing the wave, as in period and amplitude, between these two conditions and the boulders that are moved. Another important information in here is that if you look at the transition between the red and the blue, so sometimes the transition between the red and the blue is very narrow, meaning that you can pretty much average over this area and have a very, very good understanding of what boulders are moved, meaning you are very certain about the actual mass that is representative, and you have areas that take a larger mass range. And almost, if you look careful here, it's almost an order of magnitude. And that is a problem because the mass is given in a log sense. So this is kilogram, tens, 100, a ton, 10 tons here. So you see that is an issue, especially if you compare this with field measurements, because of all of a sudden you need to know these things very accurately, but we actually don't, and we can assume a certain amount of error in this. So I mentioned the roughness, so there is some bending in here. So see the importance of roughness, and you see that amplitude is important because we see that the base values increase from 0 to a few tens to single digit kilogram values here for 4, to about 10 here, or 10 or 20 in the teens, and then in the hundreds and thousands for 8 meter. And then also, if you look here for different periods, we go from here to here. So from single digit kilogram to tens and so forth. The problem now is to argue which one is the larger impact. Does the amplitude have a larger impact on the mass that can be transported, or the period? And I don't think that's necessary and important discussion to have. The importance is that we realize that both have. So we need to, when we talk about inversion, we need to look for both in our inversion models. Now we can take this and compare tsunamis and storms. And what you see here is what you call comparison. So now I change this around a bit. On X is now mass, also in the log plot. So 1, 10, 100 ton. What happened here? A ton, and then 10 tons or so and more. And on Y we have now roughness from 0.1 to 1. What this ratio is the amplitude needed for a storm wave to move a boulder divided by the amplitude needed for a tsunami wave to move the same boulder. So you can see, I think that's also like a couple million morons here. I like this kind of comparisons. So what you see is that most of the area is blue, depending on the angle of the slope. So this is essentially a downward facing slope, and this is from here to here. So from here to here is an upward facing slope, meaning that blue means that there's no difference between storm and tsunami. And as we go from blue to green, yellow, orange, and red, then more and more the storm wave have to be larger and larger in order to move the same boulder. So it's pretty simple that for flat coastlines, you may have a difference from maybe, in this case, let's say 2 or 0. Let's say 0, a completely flat coastline. The maximum difference that you see is 1.18, meaning that the storm wave has to be 18% larger, 18% larger than the tsunami wave to move a boulder of 2,000 tons and more, and a roughness of 2.2 and more. So that is quite surprising, because that is really close, and that is within the error that we have. And from this plot, you can take home that it is very difficult to distinguish between storms and tsunamis, especially for smaller boulders and small roughnesses. Even here, in this case, where we have a red area, meaning 30%, that's when we can start to see differences in the field, maybe, or able to determine differences in the field. It's only for very heavy boulders and very heavy and very large roughnesses. And that roughness here is in the area from which the boulder moved pre-transport. That means we need to know this very accurately. Let's see, look here, very accurately, in order to determine that. Otherwise, if we don't know that and assume maybe, yeah, there is exactly the same boulder in front of it, so roughness is 1, we are here in the red area, 30% difference, or we are here where we have, let's say, 10% difference, and that is a problem that we solve in the field. Now we need to move quickly, and I would like to go to a different end of the grain size spectrum. I'm going to talk about sand for just a few minutes. So sand is now our target deposit, and there are plenty of those. This is a picture from Pratong in Thailand that shows on top the 2004 tsunami deposits, and then here and here and here are older tsunami deposits that were found. There are about 700 years in between these different tsunami layers. The problem that I have personally with this is that it's great to know that there were tsunamis in the past and when they occurred, but the problem is we know nothing about the event. Was it a small event close by, or was it a large event further away? So we have no quantitative information from the deposits other than that there was a tsunami about these events. And when we think about tsunami deposits, we need to think about this. We need to think about sediments in the water column, and that makes the problem very, very, very difficult. When you see this, that's how you or other people think about sediment in the water column. It's nice and so forth, but that is very, very unquantitative. We need to quantify it, and this is when I think about sediment in the water column, that's what I see. It's not as pretty, but it is for me very useful for my purposes. What you see here is a concentration profile. Essentially, this would be sort of a concentration axis, and this is the water depth from the top to the bottom. And we have to understand that while sediment moves together, small grains and larger grains move together in the same flow, if you will, and next to each other, they are ordered in the flow very differently. Larger grains are usually closer to the bottom, and smaller grains are usually advected more in the water column. And that's how they separate, that's how they sort themselves. And we need to take this into account in these models, and that is a very, very difficult problem to handle. Nonetheless, this is not the first time we do that. It's been done for a long, long time, maybe for 60, 70 years. So we have a good understanding of what's going on in their respective equations to deal with this. What I'm going to focus on now is our how we go about inverting some important information about the causative events. In this case, I'm going to use tsunamis. So this is our modeling framework. And this is a modeling framework that is very advanced and defines actually the first real inversion model for tsunami deposits in this case, because we have a forward model that makes the deposit, and then we augment this by analysis step and bring that back into a inversion model, and we use the ensemble Kalman filtering technique, which is very heavily used in weather forecasts to help with the model results, to make weather predictions. It's a very smart way. It's going away from a single value to distributions, and essentially we do Bayesian-based statistics with it, and that gives us a way to go away from sensitivity analysis towards a real, honest, and robust error and uncertainty analysis for these models. Here is a result for a transect in India. I'm unfortunately unable to pronounce the name of the location. It was deposited during the 2004 Sumatra tsunami. You see here the locations. This is the slope that we found after the tsunami, and in these locations 1, 2, 3, and 4, we dug a hole and took took sediment samples, and then we analyzed those. Unfortunately, we didn't take samples as you see here in layers. These are model results, and it shows that the tsunami deposit coarsens from the bottom to the top, and it does that here as well. So you see here, for example, for the first one, for one, we have about 17 centimeters of deposit, and here we only have like 9-point-something centimeters of deposit, so it tempers out quite quickly. We can invert the thickness of the deposit with our model. You see here the sediment thickness with points in our model in green, and you see here in this area it predicts extremely well or it predicts, it's an inversion model, so it handcasts the deposit thickness really well. If you look at the grain size distribution in this area, and this is the grain size distribution representing the entire thickness, so all of this, not just one layer, and it's doing pretty well in the coarser portions of the grain of the distribution, and then in the finer portions of the grain size spectrum. So 0 is coarse and 6 is fine. It seemingly does worse, but actually the measurement is one of the issues in this area because of the device that people use to measure that. If we look into the inversion results, we see that we have a velocity degree. So this is 150 meters from the shoreline. This is the first deposits towards the shore, towards the land, and we see that the velocity decreases from about 4.7 to 3.7, and then that has respective consequences for the water depth. So we can invert flow conditions and then can back calculate what kind of waves will be able to produce these calculations. What we also can do with this, and that's important as well, with these very sophisticated statistical methods, we can look at the error very honestly. And in figure A, that's the error for the inversion based on different sample frequencies, meaning how many samples you take from the bottom to the top of the tsunami deposits for the flow depth, and B, the sample frequency, meaning how many samples you take from the bottom to the top of tsunami deposits and inverted for the flow velocity. And you see that the error is changing. That's the error plotted here. And you see how that the error is not constant. The error is minimized in certain area. Usually, you would expect that the more samples you have, the finer you sample, the better it is, the lower is your error. But that's not true because you make a lot more errors in sampling than one thinks. So that means we can determine an optimal number of samples that you need to take. That also means, in general, that the conclusion can be made that if your data is crap, frankly speaking, then your model can be crap as well, because of it doesn't matter if you have a high precision model and your data is very has a lot of error, your inference error in the end will always be large. So it doesn't make sense to use a three-dimensional, highly computational, very accurate sediment model for this if you cannot sample the sediments with the same level of accuracy. So that's one of the important information. But we need to get better, and we need to study this because that's not been addressed much in the literature. So I'm sort of coming to the end. So I believe that studying current events is the way to understand the past. This is something that we need to do. So we need to understand better sediment transport. Sediment transport itself needs to be better understood. We need to move away from deterministic model to stochastic model so that we can honestly and robustly investigate the error and uncertainties that are carried in the processes and then in the results in order to learn more about the tsunami deposits that we find in the past. We have such models, and that's an example from one of my students that he gave me this morning, actually, and that's for a 2004 tsunami in Kuala Wirizi in Indonesia. And what you see here in A is the water level that they measured offshore, and here's the 1D bathymetry, and this is sort of a model result here. And you see here, I cannot zoom in more, unfortunately, but you see here that like the topography before, and then what the sediment and so forth. Interesting here, though, is D, where we have in red just the data, the field data, and plotted here is the distance, and on Y is the thickness of the deposit, sort of the darker shaded gray, the darker gray area in the figure B. And in green, you see in the dashed green line here, you see earlier results with Delft 3D, which is one of the standard models for sediment transport. And in red and blue is our model, and it might be my subject mind, but I think we do a little better than what Delft 3D has done here. In any case, what we want to do is you want to take this forward model as it is. It's a combination of GeoCloud, where one of my students implemented a sediment module for us. You want to take that and implement it into this framework. That's a graph I showed you earlier. We need to replace this part here. We need to make that a real forward model, and that's what we're going to do in the future. So in summary, what I want you to take home essentially is that tsunamis and storms are often competing processes or agents of coastal destructions, especially in the area where storms and tsunamis obviously occur at the same time, or could occur at the same time. And then we need to move away theoretically in the models, or also in our understanding and our communication about this. We need to move away from process-oriented deterministic models, meaning the waves move as one boulder or something like that. We need to go, and especially with sediment transport, we need to consider it stochastically. That allows us to do much more with it, and especially, and I pointed out again, an honest and robust error and uncertainty analysis is very, very important in order to know how much we can trust in the inversion results, and how much we then, in the end, can we trust the hazard assessment that we see published. The stochastic, well, again, here, that's the point. Stochastic approaches allow for an unbiased quantification of uncertainties and error. And lastly, there's a lot of work ahead of us, but we're on the way, and we've made over the past 2 or 3 years incredible progress, especially with the availability of computational power. This has become an incredible and interesting journey. And with that, I thank you and invite questions.
Robert, thank you so much. That was a really fascinating insights into how we can look at coastal processes from tsunamis and storms. There are a number of questions, so I'm going to go ahead and read some of those, and then I'll see if Anne has any from her side as well. The first question is, what ramifications does the research have for forecasting future weather events, or perhaps more importantly, what the effects of those events will be on human settlements, and how to design in anticipation of those effects?
How far are we looking out? It doesn't matter. It was a rhetorical question. The reason why I'm asking is weather events or any event depends on the very fragile coastal system, meaning where's the coastline, how deep is the water in front of the coastline, what are the slope involved. That obviously changes with sea level change, with sea level rise, most likely. So we have no, for example, for tsunamis, I have no idea if the same tsunami in the same area, let's say it happens today, a tsunami occurs, I measure or model a certain impact. I have no idea if that would, if in 50 years or 100 years, given sea level rise, if the same exact tsunami would have the same exact impact. I don't even have an idea if it's worse or less worse because it's a very nonlinear system. In fact, we need to model this. We need to include in these predictions of future events, we need to include sea level changes, and not in a bathtub kind of way, actually model the changes of the coastline that the coastline undergoes during sea level change. And that's an important thing because of the natural system is responding to a rise of sea level in a different way that we would expect it by just rising the shoreline to the next level. So there is a way to do that, but we have been unfortunately, and I know how to do that actually, I think, but I have not been able to attract any funding to undergo this very, very risky sort of endeavor to actually do that.
So just if I could clarify, is it one answer that at least you have the fundamentals in place to potentially address this question? It's just that you haven't done it yet. You haven't been able to do it.
We believe, I would like to believe that I understand enough of the theory of waves and sea level rise that I can do that. But can I guarantee that? No, but that's what research is. Because every time I find out something new, I realize that I didn't understand that before. So I think we know to approach the question. We have the tools. We believe we have the tools. Will we be faced with surprises? Probably, but that's the enterprise that we are in, right? So, but in general, yes, we do have a good idea, at least how to start.
Yeah, and I should correct, I guess there was a follow-up from that questioner who said forecasting of future climate changes as opposed to weather events. So I think you've addressed that a little bit through your response. Let me go to another question, which is, have you run these models for boulders that are still lodged in the substrate, for example, coral heads?
So all of this has nothing to do with reality at this stage. But we could, I mean, if we know the sizes, actually, if someone sends us sizes and densities and so forth, we have no issues running these things for actual real cases. But that is not necessarily what I want. We could do that, but I think the strength of this is that we can learn a lot from running these many model runs. Because that's we get a general idea. Essentially, We just need to plot a dot in there and say, this is my boulder's weight, and let's see what it does. But conceivably, we have no issues doing that. We have not done that yet, but I talked yesterday to a colleague of mine, and they wanna, and we are in the process of setting up some models, and we'll do that obviously in the future. But we can do it. There's no issue with that. So
yeah,
we can. From a circle of boulders, essentially, we can have real boulders in there if you want to.
But I mean, from a simplistic, my own simplistic understanding, it would be a question of simply modeling the resistance to movement in a that has a greater resistance to rolling up that step, essentially. Correct?
Oh yeah,
Is that
it's just a matter of using a different coordinate systems, perhaps. I don't see any issues in changing that. For example, replacing the sphere with a block of some sort is not making it more difficult in any sense.
The other question, before I see if Anne has received any other questions since a couple minutes before, do you think that your research will help geologists understand more about tsunamis and storms themselves? Can they help make, and again, this person would like to know if it will help make better predictions, but about the impacts of tsunamis and storms. And I think you've already addressed that a little bit. And maybe I'll ask a follow-up question, which is, are you planning to look at more case studies where you could perhaps back predict, and maybe that will help gain some confidence in the models that they can predict future events?
Yes, exactly. What I would like to do is to quantify the geological record. So use the geological record, interrogate the geological record, and then produce numbers that can be used for quantitative arguments, for example, for civil defense purposes and so forth. In turn, that can be used in order to help geologists to guide their research and their methods they need to apply in the field in order to maximize both sides. The one point that I made, maybe it was a little rushed, is if we develop better models, it doesn't make it better because of the geology, the understanding of the geologist is not improved. So to some extent, this modeling that we do, the forward and the inverse modeling, is also there to educate geologists going to the field. And one of my personal goals in my life is to narrow the gap between geoscientists who go to the field in their understanding of the process and those who sit in front of a computer screen all day long, like me. That is a very important thing, because that's the only way that we increase our collective understanding of it, and then that's the only way to make it possible that people will hopefully die less frequent in the future during these events.
We're out of time, and that was the end of the questions that had come from the audience. So I want to thank you again very much for a terrific talk on a really fascinating subject and a really unique approach to the way you are doing this. So thank you again so much from everyone here on behalf of the NSF-sponsored SAGE project. And we appreciate you taking the time to give the webinar, and we appreciate the audience making the time to attend. And we look forward to announcing one more webinar later on in the spring, which will be forthcoming. So Robert Weiss from Virginia Tech, thank you once again for presenting today.
Thanks for